pretty much what I'm at. I'm almost there.
So, are you at the point where it's like, since you're getting negative data, are you at the point where you just turn into the right?
Yeah, that's pretty much what I'm gonna do. That's the only thing that I can get to. Will be it. Yeah, but there's nothing else I can do.
I think that you only got
46. Was anyone able to?
only one. I think I've only sent one. Yeah, 25 is not it. I don't even know if you're doing people doing. Somebody gave me a funny something.
Yeah, me too, man. We were just talking about it. Negative as well. Yeah, why? I just want to submit the yeah.
Yeah.
4 hours ago today?
Yeah. Like, so basically, like, only, so I did it right, but I just did it,
Wow.
and then when I tried to move it, I got out the skin,
After you gave up? What's why? You should at least submit the report to get what?
I don't even know if you can do it.
Literally, just fucking write what your prefecture, what you think your prefecture does. And that's literally what happens.
What do you think your treatment is done?
You know, yeah, but that's you literally just giving your aim out and putting it into a
Yeah, that's what I did.
yeah.
It's your happiness.
That. And part of stop answering messages. What the fuck? Yeah, this is probably.
And another thing is like, so when I type it, it's really confused, do some weird shit.
Yeah. That's another thing that I was having with Mickey Mouse my solution, to be honest.
I feel like it's just dirty.
You know, it's the well, after Thanksgiving in an American tradition is that people would start playing Christmas music, and you will feel that it's like just one day after Black Friday, all the decoration within the shop all become the Christmas theme. I don't know how that happens, but it does happen every year, and I believe it's true for this year. So to feel that kind of culture, that's why we play one of the most I would say popular Christmas song that I believe the next month, the upcoming months, you will hear it again, and again everywhere. It may not be by the same singer that I play here. The one that I play is actually the original version from George Michael, but you may hear a lot of other versions, for example, Tyler Swift or someone else. But you know, that was going to be the song that you will hear a lot again. And this is like classical research papers. Like the idea is going to be repeating again and again. And today we are going to read some of those classical papers, and you will surprisingly find that these ideas are now implemented in a lot of devices, in a lot of architectures you have. But before we start, it's always good to remind us where we are coming from. So right now, we live in a world of parallelism that all processors you have are not single. Most of the processors that you have in your devices are now not only have just one single core. It has a lot of different cores in different kind of arrangement. But the key thing here is that you have to parallelize your program in a certain way. Otherwise, there's no way that you can speed up the performance of a single process. Or say a single program, single application in your environment. And however, I also gave you quite a few demos showing you that it's so difficult to get your program right? Like we have the coherence protocol. You saw that everyone is going to see the same data, but it doesn't guarantee when are you going to see that data. Eventually, you will see it, but eventually, right? When is that eventually? It's not guaranteed. Right? So another kind of protocol called consistency protocol is trying to give you that kind of feeling, but turns out that it only guarantees that, well, you are going to see this data updated in this deterministic order from a single thread. However, the interaction among different threads, different processes are still not controlled. So parallel programming is so difficult, and I would believe that's an open problem, challenging that will be lasting forever, as long as you still want performance. Of course, if you don't want performance, we can serialize all the requests, but that makes no difference from a single thread execution. Right? So those are the open problems that you should take, open challenges you should take in mind. And because of those open challenges, open problems, on the positive side, it always give us a lot of job opportunities. Right? Like every cloud company now needs to hire a lot of you to make sure that we can parallelize those programs without getting issues. And today we are going to continue our discussion regarding why modern architecture, processor architecture looks like this, and the fundamental source is that we are now in the era of dark silicon problem. So let's talk about dark silicon and its implications on computer architecture. So dark silicon problem is actually coming from the source of coming from the fact of power consumption and energy consumption in our computer architectures. So I know that you guys must read the paper, so or at least read the textbook at some point. So remind yourself what is power, what is energy. All right, let's wrap up in 15 seconds. Yes.
Sometimes you just put the graph over there, even though it does nothing.
I think that's a good question. If I don't put this here, it's not going to be connected with the app.
What?
Yes. It's a pretty buggy software. All right, so time is up. Now look at this. Aha, we need some discussion. So go ahead, do it for 90 seconds. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. After discussion, doesn't change that much. I wonder if it's the same graph. Is there any problem with the app? No? Okay, so after discussion, you guys are kind of like insisting regarding what you chose, right? So let's see. Let me hear from you first. So regarding the first statement, how many of you think it's correct? Okay, why?
I don't remember.
You don't remember?
I don't remember which formula directly correlated with the more power that you put into more energy.
Okay. How about you?
Yeah, I think if you have more power consumption, then what does you eat?
Right. So power is directly related to heat, right? Like sun has a lot of power, right? So and another thing is that thinking about the power generator, like the more power you can generate, the hotter the core of the generator is. So same thing, right? Like if you have a pretty hot or say pretty a processor with hot power, which I think I should put a video in a slide that show you how a processor can heat up an egg, which I believe a lot of you must saw that on YouTube, and I'm not kidding you. It's actually true, right? So lowering the power consumption helps reducing the heat generation. That's definitely true. How about the second? Lowering the energy consumption helps reducing the electricity bill. Yes, right? Because energy consumption, if you think about how the electricity is calculated, is like how many power you consume over a period of time, and that's the exact definition of energy. Right? So energy consumption is related to electricity bill. So 3, lowering the power consumption helps extending the battery life. Yes, no, okay. A CPU with 10% utilization can still consume 33% of peak power. Yes? Okay, so at least 3, right? So, but interesting, right? Like we saw the most popular answer was D, but it seems like most of you are kind of like with D or E, right? So let's examine the last 2 statements first. Okay, so everyone has a consensus regarding the first one, right? So, okay. Okay, power is the direct contributor of heat, and because of the hotter the chip, power actually also affect the packaging cost of the chip. And thinking about if you have a hotter chip, it takes quite a lot of effort in material science to figure out how to cover this chip properly to make sure that the heat dissipation can be done appropriately, so you won't burn your motherboard, you won't make your computer like a heater in a room, right? So that's the first thing, right? And the second thing is like heat dissipation cost. Again, right, as I said, if you want to dissipate the heat, well, sometimes people even really need like water cooling system. That takes a lot of money, right? But where the power comes from? So power actually composed of 2 different factors. And previously, when we talk about why we go into multi-core architectures, we talk about the dynamic power, but there is actually another part called static power, which would be part of the main thing we are going to talk about today. And what is energy? As we mentioned, the definition of energy is the power over a period of time. So it's the aggregated power over a period of time that you consume for a certain task or for the total system. So the electricity bill and battery life, because thinking about what is battery? Battery is actually the storage of energy. So the more energy consumption, the shorter the energy life, the battery life, right? And lower power does not necessarily mean that you are going to lower the energy consumption. So, so here I have a demo for you. Okay. So, we have been learning that you are able to change the maximum frequency of your processor in the past, right? So you guys all buy this. So now I'm going to give you an example. So there is a program called Liquid, which allow us to profile the energy consumption power information from those performance counter on your processors. So here I'm on an Intel machine, and I already wrote a script. This one is called Energy, and it's called the Liquid the program, which try to dump the energy for a program that I invoked. So let me do this. So let's try. One of our favorite program was, let's do
mattress multiplication, which is probably one of the stars that we have been talking about in the class for a while, and we want to use the block MM version so that you won't feel like I'm running a very slow program, right? So let's try this one, and we are running it at the original frequency of the processor. So if you look at the result, right, it shows that, well, for now, we are having the processor itself dynamically switching between its maximum frequency around like 4.4 gigahertz and the lowest frequency, which during the idle time it was 1.3, and the average frequency here is 1.7. Right? Remember this number. Right? The average frequency right now is 1.7, and the energy consumption we have is 3.2 joule, and the power consumption is about 26 watt. Right? That's where we are at. Okay. So now I am going to run another script which lower the maximum frequency, and I set all the 6 cores to be only 1.2 gigahertz. And now what I'm going to do is that I'm going to run the same program again. Okay, so now looking at this, right? The minimum frequency we have here is 800. And the maximum frequency here we have is only 1.2 gigahertz. The average frequency here is simply above 1 gigahertz. So the power consumption is 8.3. But looking at the energy consumption, 3.64, and what was that? 3.23, right? So previously, although the power was at 26 watts, but your energy consumption is only 3.2. But right now, I slow down, or say lower the frequency of the processor, so I can make the power consumption to be only 8.3. But turns out that you are spending more energy on it. Another program that I can show you so that you know this is not a simple case, simply the case, right? So you might say that, well, you know, for mattress multiplication is memory intensive, so I don't buy your idea. Okay, let's try pop count. Right, pop count, as you know, at the end we can eliminate all the memory references, so it becomes purely computation bound. Right, so this one, remember right now we are running at the lowest, not the lowest frequency, but at only 1.2 gigahertz. And it takes a few seconds. Okay, see, so for this program, well, because we clock gating the processor, so the processor is running at 1.2, right? And power consumption, 8 watts still, and finishing the whole program, 152, right? Now, I restore the maximum frequency. So it's all going to 4.6. And let's see what happens. So it was 8 watts, 152. Right now, see, the program finishes faster. The power consumption is 28 watt. The energy is only 142. What does that mean? Lower the power consumption actually increase your energy consumption. Why? Remember this, right? Power consumption is, power consumption is what? Energy consumption is power times execution time. Right? So if you lower the power consumption a lot, however, your energy still goes up. Means that lower the power consumption actually make your energy execution time goes up a lot. So that's actually not a good idea. So in the past, a lot of people they chose to design that I have a laptop with very, very slow frequency, and they thought it's going to make the power consumption lower. That is true, because in that case, at least when you put your laptop on your lap,
it will give you a tolerable temperature. However, in terms of a battery life, that's probably not a good idea, unless and for example, right, the same task you have to spend more time to finish it, and turns out that you will have to spend more time in making your slides, in typing your documents, and the user experience is not great, and it's also not good for your battery life either. Right? So so that's a myth that we have to get rid of first. Right? So power consumption, lower the power consumption doesn't mean that you are having better better energy consumption. I wonder if there is a case that I can see the power consumption right now. Okay, another thing to think about is, right, like, so now looking at this question, right, we know the third one is not correct. Now, a processor with 10% utilization can still consume 33% of the power. How about this one? Why is this true or false? How should we be looking at this? Because we have stated power. Right? So looking at this, power consumption is consuming of two parts, right? As we mentioned, static power and dynamic power, right? And in modern technology, most of our processors right now are manufactured within even smaller process technology. This one is 20 nanometer, right? So for 20 nanometer, it tells you that the leakage power, which is the static power, is almost the same as your dynamic power. Meaning that as long as the transistor is connected, it's consuming power. Right? So 35% is actually underestimated. In fact, half of the power comes from a leakage power. And what's leakage power? So remember, there's nothing perfect in the world. So all the transistors are not perfect. In a way that as long as you give it power, as long as you connect it with electricity, it's leaking. It's like water pipes. No water pipes never leaks. So again, right? Like this electron, they escape. And it's not a big issue in the past, not because they don't exist. It's just because in the past the dynamic power is so significant that this leakage power is not significant. But right now, because the process technology improves, so it keeps improving the dynamic power, but the static power cannot improve significantly with new process technology. So even though the static power doesn't increase, but because the dynamic power decreases a lot. So that is like the Amdahl's law. Right? When we address the most significant problem, then the insignificant part becomes more significant. So static power becomes the dominant factor of the computer architecture right now. So it turns out that even though I'm not doing anything, I may still consume half the power as the fully powered process. So that's the issue. So 3 of the statements are correct. The only one that is not correct, and that's actually the myth that a lot of us might get into, is that the power consumption doesn't have, it does affect the energy consumption, however, not necessary in proportion or on the positive side. And in most of the cases, like I randomly picked 2 programs, and this 2 programs shows you that lower the power consumption is not a good idea for energy consumption.
All right, so we know this, right? And now I have another question that might need you to think a little bit more. So why don't you read those statements and tell me what you think? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. What do you guys think? Okay, looks like we did some discussion. So go ahead, discuss with your friend for another 90 seconds. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, looking at what do you guys think after discussion? Oh, seriously, C and E still. Okay, so it's either oops, it's either 2 or 4, and unfortunately because my animation, so I kind of like reveal the answer. All right, so why the first one is correct? Can someone explain that? Why do you think the first one is correct? Right, so you have more transistors with the same amount of power within the same area, so the power density does increase, right? And the higher the power density, the more problematic of your heat dissipation, or you just cannot have so many transistors within the same area. Otherwise, you will have to change the way how you dissipate the power, right? So the first one is correct, and why the second one is also correct. Oh, sorry. The first one and first, I was saying about the second, right? And for the first one, right, the same chip, if you have more transistors, the power consumption. How about the third one? Give the same power budget, we may not be able to power all the chip area if we maintain the same clock rate. Yeah. That's true, right? Because if you can only, if this is the amount of power you can provide to this processor, for example, I have a power budget for 125 watt per processor. If you have more transistors that consume, turns out more than 125 watts, the only thing you can do is what? just that those additional ones that are dark, right? I cannot power them all, right? So here, here, you hear the word dark, right? Now, given the same power budget, we have to lower the clock rate of circuits to power all chip area. That's the same thing, right? Remember what? Kinetic power that's related to your voltage, right? So if you want to power them all, okay, slow all of them, right? So these are the reason why you see a lot of processor designs like this nowadays, and we will talk about those trends. And the first paper that points out the problem is by is led by Hadi, and he's now a professor at UC San Diego, and the paper is called Dark Silicon and the End of Multi-Core Scaling. Right. So previously we said that, well, we shifted from single core to multi-core so that we are allowed to leverage the increased amount of transistors that we are able to accommodate in the same area by using them as a separate but simpler cores, right? And in this way, this parallelism can still help us to improve the performance. However, that was not true anymore at some point after we see the leakage power is trying to dominate, right? So what's wrong with that? So actually, Moore's law continues. However, the Dinardian scaling broken. So what does that mean? Is that classically, if you don't consider the leakage power, the per transistor power consumption is like this. So scaling factor means that by how much you can shrink this a single dimension of your transistor. And in the past, right, the supply voltage, a lot of parameters, they go with the scaling of your process technology. So for example, if I can cut it down from 14 to 7 nanometer, I'm able to cut my voltage. However, because right now, leakage power becomes a dominant factor, and that doesn't scale with your process technology. So it turns out that, yes, you do make your transistors smaller. However, the leakage is still like that, right? So voltage doesn't go down. Turns out that saturation current doesn't go down, and per device power remain constant, right? And the chip power becomes more because you actually can accommodate more transistors within the same chip area. And the utilization, if you give the same power budget, it means that only this small amount of transistors can be powered on if you don't change your power budget. That's the consequence, right? And as we can remember, right, as we can imagine, right, given that if I have a chip with 15 watts power consumption budget, right, in the past, if each transistor is about 1 watt, I can power 49 of them. Now, if Dinardian scaling continues, what it means is that, okay, if I improve my process technology, I can potentially put twice more transistors with half the power consumption of each transistor. So I can technically put 100 of them, but consume only 15 watts. However, with broken Dinardian scaling, right, if I want to power them all, it takes about 100 watts, which is surpassing my power budget. So it turns out that I can only on part of them, but that the other part off, right? So the off part is like dark. So that's why we call it dark silicon problem. And because of that, right, the clock rate improvement is also limited, as we mentioned, right? You're not able to scale up the power. You are limited in power. So it turns out that your clock rate cannot grow up very significantly. So as you can see, in the past, we got 15, 40, but now it's only 2% per year. So we haven't seen processor, commercialized processor that is able to run 5 gigahertz for quite a while. We saw this happening 20 years ago,
But turns out that it's not there, right? And the reason is just because of this, right? But in fact, a lot of people say it's because Moore's law is dying. But from my explanation, for those people say that simply say Moore's law is dying, they don't know computer architecture. It's true that Moore's law is slowing down, but surprisingly, people still improve the process technology. As you can hear that TSMC, Intel, they are trying to roll out the next generation of process technology still. However, I mean, they are still able to shrink the size of the transistor, but it's always a problem for them to put those into mass production is because they're not yet stable. And it makes no benefits for them to shrink the process technology anymore because it's not improving power consumption, and investing in new manufacturing technology means that they have to spend a lot of money to upgrade their devices, which makes no sense for them. So if you want, Moore's law can still continue. However, if you don't get rid of the dynamic scale problem, I see no reason why people should pursue better process technology. So that's why you see a lot of chips, they are now satisfied with not the most advanced process technology because of that. Because I don't see any benefit of moving toward the new process technology. And plus, using the latest process technology potentially give me worse yield of a chip, higher the cost, and resulting in shortage problem. And that's probably one of the reasons you see there is a huge shortage in chip GPUs right now. Okay, so if you cannot get rid of the problem, the only thing we can do is live with it. So let me show you how we have been thinking about living with it. So here are some solutions trends in dark silicon era that you might already feel. So in my opinion, there are 4 trends that we see. The first one is aggressive dynamic voltage frequency scaling. So from the demo that I just showed you, when I run a top-down programming, our processor frequency actually jumped all the way from 1.2 to 4.6. So it shows that right now, your processor is able to adapt to the characteristic of your workloads and to figure out what's the best thing to do to adjust the frequency. Of course, there are lots of papers on this. If you're interested, embedded system class or a lot of different classes offered by either the E department or the computer science department might talk about those technology mechanisms or policies, how they adjust the power. So it's out of the scope of this class. But one thing I want to tell you is that from the demo, right? Even I don't do anything, even though I already restored my frequency to the maximum frequency, it's just the maximum frequency. All the rated frequency right now is either the maximum frequency or the base frequency. Your processor in the background would dynamically adjust from the lowest possible one to the highest possible one whenever it's appropriate. The second one is instead of fighting for the shortest latency, we fight for throughput. So a lot of design in microprocessor, you see, is latency oriented because we want to finish a task, we want to finish the instruction as soon as we can. That's why we have the cumulative execution. We have a lot of techniques. However, if we cannot make a single thread faster, the only thing we can pursue is make it throughput oriented. Is that, well, each task becomes slower, but in the meantime, we can finish more. The third one is, well, let's accept the fact. If eventually this is what we can turn on, let's just let other parts dark. Let it dark and only activate parts of the circuit once in a while, but not all of them. But what kind of architecture would look like? And finally, from general purpose to domain space. So in the past, our goal is that we want to design processors that fits all tests. But that turns out there is a huge cost of making things general purpose. So what if we make our processor application specific instead of general purpose? So those are the trends that we are seeing nowadays. So the first one I'm saying is aggressive dynamic voltage frequency scaling. So for the modern processor, right, this is a Core i9 Coffee Lake, which I think is the same generation as the one that I show you in the demo, right? I'm using a different processor, so you might see the frequency is different. But as you can see right now for the processor spec, it has the base frequency of 3.6, but there's a turbo frequency of 5 gigahertz. Question?
How will it decide which transistor to make it dark? Is it the same transistor being every time dark?
We can talk about that later, but right now we are at the topic of frequency scale. But I can say it depends on what kind of test. Yeah, we can talk about that. Okay, so, and you will see a technology here is turbo boost. So turbo boost is the technology that it's kind of interesting, right? So here, you remember that the total power consumption of a single processor is limited. And the turbo boost technology is kind of interesting in a way that, okay, if you only have one program that you are running and you really want it to finish fast, if that's the only compute intensive program in the system, what I would do is that I would make all other processors really slow, but make that single core really fast. So in this way, one processor may be able to run at 5 gigahertz, but in the meantime, all other processors may have to run at a really slow speed to let one processor run really fast. So that's the model of turbo boost, right? So this technology shows that an example of aggressive adjustment of frequency in your processors. So that's one trend, right? And the reason, and this one, it doesn't help static power that much, but at least it helps the dynamic power steal half of your power consumption. Right? So in this way, as long as you lower the power consumption, you are able to control the total power budget. And if you are maximizing your power on a single core, it makes your program, that particular program, run faster. It doesn't make the energy consumption of the total system worse. Right? So that's the idea of turbo boost. However, that only with dynamic frequency scaling, that only address half of the issue. Another half of the issue is about static power. How can we address that? So the second part, which I think is a trend right now, is called slow but more. So one of the examples that I can tell you is the paper that in the assigned reading. If you don't know don't remember the paper, shame on you. Right? So this paper is called Single Instruction Set Architecture Heterogeneous Multi-Core Architectures, the Potential of Processor Power Reduction. It's by Rakesh Kumar and Noam Jopi. Do you remember him? Right? And Victim Cash, right? And we talk about right? So and Pasa, he is actually a very prestigious architect in HP Lab used to be, but right now he is with Google. And Noam Jopi is also with Google right now. One of them is now designing the architect for the Google's cloud servers, and the other is like Noam is leading the project of tensor processing units. So they are pretty significant computer architects. Dinkhausen, advisor, right? So, and this paper was published in 2003 at a conference called Micro, and this year it just got the Tesla Time Award. So this is a really significant paper. So what this paper is talking about,
right? So this idea, and surprisingly, right, 20 years ago, people already have the idea to tackle the issues that you are seeing right now. So let's see, right? So this paper is kind of interesting. So, that was still an era that people thinking about how can I make a single core performance really good, right? So you can have a processor like this processor architecture called EV6 Plus. Is a wide issue processor with very good bridge prediction, and so it can accommodate 4 threads in parallel. But turns out that the area of that processor is about 30, right? So 30 millimeters squared. So with the same area, you have actually other choices. You can actually put, okay, if you want to build a quad core, so you can, yeah, so if you want to build a quad core EV6 processor, so which means that you are going to have a total of 120 power budget, right? And this is about 24. So you can actually have 3 of those plus 5 of the small ones to be within the 120. Or you can build a 20 core EV5. They all give you the same area. Instead of having 4 of this powerful cores. So these are the design decision alternatives that you can make if you are given this amount of. So what it is thinking is that, okay, if I chose this alternative, what my performance would look like? Can you project? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. So what do you guys think? We really need discussion. So why don't you go ahead and discuss with your friend for another 90 seconds? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, C is more popular now. So let's hear from you. What do you guys think? Regarding the first one, what do you think? Do you have to recompile the program? Why not? Then microarchitecture? Is the microarchitecture the right word? What's the definition of microarchitecture?
How do you organize all the elements?
Organize the elements. So if I have a single instruction set architecture, heterogeneous multi-core architecture, what's the same? What's different? Instruction set architecture is the same. However, microarchitecture is different. So, and the whole purpose of the paper is what? You actually can fit more cores with elder generations of microarchitectures inside the same area, rather than put the most advanced one, the most power-consuming one, in the same area, right? So, do you need to recompile? You don't need to recompile the program, and the main reason is because of what? It's the same instruction set architecture. So the same program doesn't need to recompile. So for example, the same x86 program, if you compile it on Core i7 7000 the 7th generation, you don't have to recompile it. On the 9th generation or the 11th generation, the same program still runs. Not the other way around, but most of the time, if you compile it on elder generation, it does work on your generation. So you don't have to recompile the program. How about the second one? Limited thread parallelism. Yes or no? Single instruction set architecture heterogeneous chip multiprocessor would deliver better or at least the same level. You think it's correct? Limited thread parallelism, single instruction set architecture, heterogeneous chip multiprocessor would deliver better or at least the same level.
Two words that are very. The first one is limit, second one is batch. I'm not sure what the limit is.
Okay. How about the third one? For a program with rich threadable parallelism, means a lot. What do you guys think about this? It's true because you have more cores. Okay. Spending more instructions on older generation cores always lead to better energy. Yes. No. Okay. So that's why we need a paper, right? This paper provides a lot of experiments to show you that. So one interesting metrics that this paper is using is called energy delay. So previously we only talk about energy. We only talk about delay means the end-to-end latency of running a single task. But sometimes we do want to find a trade-off between them. And as we mentioned, there are cases that where you lower the energy, and remember, the energy consumption is the execution time times your power consumption. Right? You could lower the power, make the energy consumption longer, but make your energy less. Sometimes, most of the time we see it's increasing, right? And sometimes we do think performance is important, so we want to wait. By wait I mean, right? Wait, right? So we want to wait the execution time more. So energy delay is actually power times execution time. This part is energy, and times execution time more. So through this, you will feel that the weight of execution time is actually more because execution time is more directly related to user experience in most of the cases. So looking at the table, right? So first of all, looking at the table, right? What do we see? So first of all, the performance loss, 3.4. So one interesting thing is that can program with some sort of parallelism surpass the performance of the baseline. By looking at this. So for the testing program, they have never measured. So it never surpassed, but at least the same level. For programs with limited power. Well, so this is actually, okay, I guess I'm wrong. So this is a program with one thread. Right, so what the experiment is doing here is that I dynamically change the core that I'm running the test. Right, so for each single thread, if you switch a run, right, it never surpass the performance of the single core. So this gives you an idea that if you have limited number of parallelism, then it's hard to surpass the performance of a processor with more advanced technology. Right? And that's one thing. However, if you look at one interesting trend is that if you spend more, as long as you spend more instructions on elder generations, you start to see energy savings. Sure. And surprisingly, because the performance loss is pretty controllable. So energy delay, at least from this list, is always better. Okay. Another thing that we want to see is that the horizontal axis of this graph is the number of threads we have in a program. And the vertical axis is the weighted speed up from those applications that we just showed. So looking at this, this is the single instruction set architecture, heterogeneous processor. And this is a homogeneous processor. And this is a homogeneous processor with newer generation. So let's look at this. This is our. So that's a very interesting part. The statement is kind of tricky here. The program is limited parallelism, single instruction set, heterogeneous chip-only processor. Better or at least the same level of homogeneous. So there are two types of homogeneous processors. One homogeneous processor is what? One type of homogeneous processor is this. So this is the one with the most advanced cores. And one type of that is this. So what do you learn? The answer is kind of interesting. So if for the program, for this single instruction set architecture heterogeneous processor to operate, as long as you are within this range, which is kind of like a limited parallelism from some definition, right? We could actually get better performance, right? But it's within a range. However, if you have really rich parallelism, right, then what happens? If you have more parallelism than that, the idea is looks like if you have slower but more cores, will be better. If you have rich parallelism, right? So now looking at this question, you don't have to recompile this. And for a program with better, with limited threadable parallelism, yes, right? For a program with really rich threadable parallelism, are we able to survive? Not really, right? Spending more instruction on elder generation cores will always lead to better energy delay. That's a very dangerous, right? So if you are talking about a thing, I would say the always is a very dangerous word to say, right? It looks like from the experiment that it's possible. However, this statement is actually broken in a certain way that it doesn't talk about if the program is a single-threaded one or parallelized. And thinking about execution of parallel programs on if you are remember this, right? If you are at this part, right, then using the most advanced core may be a better idea. So I would say the fourth one is questionable, but the only one that would be correct is probably. So now, this is a very interesting thing. So, but fortunately, most of the time, how rich the parallelism can you find from a single application? Not that much. So it turns out that it's always a good idea that, at least for our daily usage, we could leverage the idea of single core, a single instruction set architecture, heterogeneous multiprocessor to get the best energy delay or to balance the energy and the latency for the program that we are running on the everyday workload. So one of the earliest implementation is ARM's big little architecture. So ARM's big little architecture is pretty much the implementation of the single instruction set architecture heterogeneous chip multiprocessor that we mentioned, right? So so for this example, they have 2 big cores plus 4 other little cores. So those other little cores, they are able to execute multi-threaded programs efficiently. And those 2 big cores, if you have a single-threaded one, we will put them there to make sure those single-threaded programs can run more efficiently with big cores. And because they are the same instruction set architecture, so all you need to do is to have a coherent interconnect, and they share the same memory architecture without any problem. So that's the beauty of single instruction set. A single instruction set architecture, heterogeneous chip multiprocessor, is that because they are the same instruction set architecture, the only thing that is different is the microarchitecture, which is transparent to the programmer, to the rest of the components on your processor. So we can easily put them all together within the same core, and that would allow us to leverage, although not, you can never say that I can in favor of parallelism, of single thread performance, and this kind of design. But the good thing is that you can balance the energy delay in this design. So this design is interesting that it doesn't optimize for parallel program. It's also not an optimization for latency. It doesn't give you the best throughput. It doesn't give you the best latency, but it gives you the best balance of energy consumption and latency, or in fact, energy design. So sometimes when you design system, you are not aiming at one extreme end. You are aiming at the balance in between them. So this big little core, or in general, a single instruction set architecture, heterogeneous chip multiprocessor is aiming at. Another trend that is also similar to that is that, well, you see, right? If you really want to accommodate the case where you have programs with rich parallelism, the best to do is what? Putting a lot of slow cores in your system, right? So for those of you would see is that, remember the frequency we talked about, the consumer product processor, right? The turbo frequency is at 5 gigahertz. The base frequency is at 3.7. But looking at those server processors, which a lot of you might have in the lab, or a lot of you might use this kind of processors in Amazon Cloud. If you have a 24-core processor, the frequency is only 2.2. The turbo frequency is 3.4, right? And if you have a quad-core processor, which is a lot cheaper, right? Then the base frequency is actually higher. And the main reason is what? Because we have limited power budget. And it's also another indication from the paper that we just read. If you want to put more cores within the same area with a limited power budget, right? Then the only thing you can do is what? Slow that down. So that's another indication. And this is an example of Xeon Phi processor. So it has 72 cores, and the frequency is even slower, 1.6, right? And another example that I can give you is actually your GPU. So a lot of you still have the myth that GPU is the most powerful hardware for now, right? But let me show you this, how slow your GPU is. So your GPU, your graphics clock rate, right, is only at this fast, right, 2 gigahertz, right, not faster than your processor, right? The processor we have, the base frequency is 3.7. So GPU is actually another representative of slow but more. Because it's slow, so we can accommodate that. All right. Right, so GPU is one of the examples, as far as you remember, right? Each of this, they are really slow. However, because we have a lot of them, so our throughput is really great. Now, the second trend I'm talking about is just that it's dark. So one example is like the Nvidia's Turing architecture. So in addition, so right now, if you see the Nvidia chip, right? Each stream multiprocessor not only have the floating point 32 CUDA cores. It also has the integer part, FP64 part, and also another thing called TCU, tensor cores. So these tensor cores are used for mattress multiplication only. What does that mean? If today we are not doing mattress multiplication, this part is not used. And what can we do? Turn it off. That's what we can do, right? So if you think about how to program, right, in Turing architecture, is that you have to specifically tell the GPU that I'm going to use tensor cores. And in the meantime, the runtime system in your programming model will know that, okay, you're going to use tensor cores. Give me a second, let me turn it on,
right? And then I can turn off the rest of the part. To schedule your task specifically onto those tensor cores whenever the function is called. So this is one of the examples in modern architecture is that you have to tell the system what kind of accelerator or what kind of component I'm going to use in the rest of the computation. And of course, for tensor cores, because it has its limitation on the supported data precision, so you have to explicitly convert the data type to 16-bit, because so far it only supports 16-bit input and aggregated into 32-bit. So when you are executing the program, you can only use either type of this ALUs, but not all of them. Right? So for example, if you compute on integer, I'm only going to use this part, but the rest part, I can dynamically turn it off. To then it's dark to save. So that's another trend. If I have dark silicon problem, I just let it dark. And I know the task you are giving me is either this, but not all of them at the same time. And as you can see, right now the target of GPU is never running multiple tasks at the same time. It's focusing on maximize the throughput of a single task. So this model is okay for it. The second trend is just like that it dark. And the next trend is ASICs, application-specific integrated circuits. So, for example, say that we want to implement a circuit like this, right? AI plus equal to AI plus 1 times 20. So, for example, if this is the task you are doing, right, you can have a RISC-V instruction, a sequence of RISC-V instructions like this. To implement this, you will have a total of 6 instructions, right? And the resulting pipeline diagram will look like this because you still have to handle those hazards, right? And you have different types of instructions. But what if I want to spatialize the circuit that I know AI plus equal AI plus 1 times 20 is the only thing that I care about for this processor? Then what a processor design would look like. So first of all, because I know every time you only want this type of instruction, so I can simplify the instruction fetch. And in fact, this is the only function you want, right? So whenever you have data in, I know you are going to run this test, right? So we don't need instruction fetch unit. Okay, we only need a signal to tell us that you have data in, right? Now, in that case, right, you don't need this many registers anymore because all you need is a space to store AI plus, right? AI plus 1. So you don't need many registers, and because you are only having one type of instruction, you don't need to you don't need very complex circuit to decode. This is what it ends up looks like. All right, ALUs, because you are only going to do plus and multiplication, right? So, and you don't have branches in your program, right? So branch predictor, branch unit, you don't need them. Okay, now, these are the remaining data paths you have afterwards. You only need a plus A to advance to the next unit. You only need times 20, and it's a constant. Okay. So this is the data path elements you end up with. And what you can do is that you can still pipeline them in this way, right? So you have an instructions, you have a sequence of AI plus equal to AI plus 1 times 20. So you can actually pipeline it in a way that different parts of them are computing on different data elements. And the beauty is what? Remember, each of these instructions were originally 6 MIPS instructions. So in the same way, you can think about right now. In the past,
I can only run 6 instructions, but right now I can have 24 instructions that are performing exactly the same task in the same basis. So and plus, this circuit is simpler, so your frequency could be higher. And even though I'm maintaining the same sequence, considering what I said, 6 instructions, but now 24. You have 4 times speed up with application specific IC, right? So that's actually why right now you see a lot of papers are talking about application specific IC because they could be more efficient. So the next lecture will be our last lecture of the quarter. There will be a lot of things we will be doing. We will probably take a group photo together if you are okay with that. And we are going to give you the sample final. But before we get into that, a few things that I want to let you know. I know project due tonight. A lot of you spend a lot of time. I would say try your best. Try your best. Right? We'll figure out the grades. Don't worry about that too much. Right? And assignment 4 due this Wednesday. If you look it up, it's a pretty long one. So if you end up give up, remember that once you've done the I-eval, you get a full credit assignment, and we are dropping 2 of your lowest ones. So if you feel like, yeah, this is a really long one, and I have done a good job on previous assignments, you can probably give up on the assignment 4 so that our TA will be happier, right? And you will be happier. But don't forget to go through the solution after the deadline, because some of the questions might end up being in your final exam. And the final exam is actually, I'm going to give you quite a lot of flexibility, but this flexibility doesn't mean you can discuss without it. You have to done it individually, and you will be surprised whenever you discuss with people how similar your answers are. And I always said, if I find any of those, and the most direct thing I will do is that I will zero out that, I will file your case to the misconduct for investigation. Another thing that I want to say, I typically would like to take a break after the final, so you won't be able to find me. I will not be responsible for email. I want to have a 3-week break because I really need to fresh myself out. I don't know where I am. I was thinking about Hawaii, but it turns out that being a single person going to Hawaii is actually another torture. So I'm still thinking about what's the best place to go. But somewhere around the earth, I hope I have sufficient money to send me to the space. If possible, I will definitely do it. But not at this point. But one thing I want to tell you is that don't try to cheat. And I won't, the consequences is not something that you can do. All right? And so you are going to give, and I'm giving you a pretty flexible schedule. From this period of time and any consecutive 3 hours, you can find 2 problem sets will be comprehensive exam questions, and sample final will be the end of the class lecture. Other than that, enjoy the rest of your day. We'll see you on Wednesday.
The project, can I discuss with you right now for a couple of minutes?